Hi everyone, welcome back to another video. In this video, I'm going to talk about the electrical properties of solids, which means we are going to talk about what are conductors, insulators, semiconductors, also about the band theory of conduction, and also about the N-type and P-type semiconductors, okay? Looks like we have a long day ahead, so let's begin. Alright, so before starting, we should know what actually is conduction, okay? So conduction is an inherent property of a solid. What is inherent? Inherent means that it is inherent to it whether or not it is going to allow the passage of electrons through it, okay? For example, everybody knows that copper is a conductor. I think everybody knows. Copper actually forms all the wires, and we have all the wiring system in our houses made up of copper most of the times, okay? So copper is a conductor, we all know that. Whereas if we talk about wood, okay, everybody knows that wood is not a conductor, right? Because no matter from what place of the earth we import the wood, wood is never going to be able to conduct electricity. It is going to burn off, but it is not going to conduct, okay? So that is why wood does not fall into category of conductors. It is inherent to the wood that it is not going to pass, not going to allow the passage of electrons, right? So on your screens, you can see there are certain materials which are added into the circuit, and where if the bulb glows, they are conductors, and if the bulb does not glow, they are insulators, right? So on the basis of this parameter of whether or not they can conduct, the materials are actually classified into three, okay? The first one is conductors, which means they conduct electricity nicely, okay, without any issues. And examples are all the metals, okay, mostly. And then we have insulators. Insulators are the materials which do not conduct electricity no matter what, okay? Example is wood, glass, okay? And then we have semiconductors. Now, semiconductors are a little different, okay? They may conduct electricity given certain circumstances. And we are going to discuss as a part of this video, what are those circumstances and when do they conduct electricity? So let's start. Now, when we talk about conduction, well, conduction happens due to movement of two things, okay? So what are these two things? So when a material is having free or delocalized electrons, so every system has electrons, you should know that, okay? If there's a sigma bond, these electrons are tightly bound and they are not available to move, okay? So the most important thing is that the system should have free or available electrons, and if that is the case, then the material can conduct electricity, right? The second thing which the material should or may have for conduction is the ions. So in case of metallic solids, we have free electrons, because of which metals are conductors, right? But in case of ionic solids like sodium chloride, we know that when sodium chloride is mixed in water, we have sodium and chloride ions which are formed, and that solution is also a conductor, right? So again, ions also, the free movement of ions, the mobile ions can also cause electricity conduction, and these are the two things which are the main reasons for, not the main, but the only reasons for conduction of electricity in any material, okay? But as a part of the band theory, which we are going to discuss as a part of this video, we are going to talk about only the materials which conduct electricity due to the presence of electrons, okay? So let's start. Well, before starting, we'll talk about the metallic solids for a bit. Now, metallic solids, as we already know, have an electron C model. What is an electron C model? Electron C model is like the positive charges. So, for example, we have sodium, okay, which is a metal. It is going to ionize into sodium plus and one electron, okay. So, this is called the cation, or we also call it as kernel, okay. And this is the one electron which is present. In magnesium, we have magnesium plus 2 cation, and here we have, instead of 1, 2 electrons, right? So this is magnesium kernel, and we have 2 electrons per atom. So in case of metallic solid, we have number of valence electrons which are available per atom, and the more number of electrons we have, the more conduction is going to be there in case of metallic solids, okay? Now let's talk about the band theory of conduction, and the band theory is going to explain what is a conductor, what is an insulator, and what is a semiconductor. Alright, so let's discuss what is this band theory, okay? So this band theory is actually a theory which tries to explain the conduction in case of your various conductors, insulators and semiconductors, okay? And it is based upon your MOT, which is the molecular orbital theory, okay? What is this molecular orbital theory? This theory basically states that whenever atomic orbitals combine, okay, of equivalent energy, they give rise to new orbitals which are called molecular orbitals, right? That's what this theory basically, this is what it has to say. Now, we all know that every element in the periodic table have certain valence electrons. We know that, right? Metals have valence electrons which are quite loosely bound, but all the other also have valence electrons. हैं तो सही, ठीक है? Loosely or not loosely bound. Now, these valence electrons present in any kind of system are so close in energy that they are going to form a band kind of structure, okay? So this is what they're going to form because they are in so close in energy. These atomic orbitals all combine to form molecular orbitals and they are so close in energy, they form a band, okay? And this band is called the valence band. Valence band is made up of all the different valence electrons which is available in case of any element, okay? Okay, now the band theory says that a conduction is possible, okay, in any material only when the electrons from which, of course, you know the valence band is filled with electrons, right? So when the electrons from the valence band can cross this energy gap and reach to the conduction band, okay, that is when conduction is going to happen. This is what this theory has to say. Now, the most important thing for you to realize is there is no actual band, okay? There's no, actually you'll not, if you just look into a conductor or insulator, you will not find a real band there. No, it's actually just a theory which is trying to explain conduction, okay? There's no reality of band or all these things, okay? That's something which we should know at the back of our minds. Okay, so when this valence band is there and when the electrons from the valence band are able to cross this energy barrier, okay, and reach to the conduction band, that is when conduction happens. Okay, so it's quite a given that of course in metals, of course the electrons maybe can cross this barrier, that's why metals are conducting, right? In insulators, maybe the electrons can never cross this barrier, that's why they're insulators, they do not conduct. And in case of semiconductors, they may sometimes do that and may not, right? Okay, so that is what this theory has to say. So whatever I just said, I'll just put it into, words in a better way. So in metals, as you can see, this is the valence band, which is the filled valence band. So valence bands are always filled because every element has valence electrons, right? So valence band is always having electrons. But the question is, does the conduction band have electrons? And if that has electrons, only then conduction is going to happen. So in valence band, as you can see, in metals, these two bands are overlapping. Okay, so there is no energy barrier which the electrons have to fulfill. Electrons are so easily moving to the conduction band that conduction is readily happening in case of metals, right? So in case of metals, there is no energy gap or maybe a little energy gap which might sometimes be there, and that is why conduction is very easy in case of metals, okay? Talking about insulators, okay, the valence band is having certain electrons, but there is a huge energy gap which is never possible for the electrons to fulfill, and that is why insulators never conduct electricity, okay? Whereas in case of semiconductors, as you can see, the energy gap is quite little, okay? So the electrons cannot readily go to the conduction band, but if they are provided with certain amount of energy, they can do that, right? So that's why semiconductors, because they might conduct electricity, they might become conductors in certain conditions. Okay, now what do you think would happen when we increase temperature for metals? Right now I'm only talking about metals, I'm not talking about semiconductors or insulators, okay? As I already said, if in semiconductors we gives the electron certain amount of energy from ourselves, from our side, which may be heat energy, the electrons from here can go to here and become conducting in nature. In insulators, if we apply energy, still they will never be able to cross this barrier, and no matter how much energy we apply, insulators is never going to become a conductor, okay? In metals, what happens? Let's say, because in metals already conduction is happening, right? But in metals, if we try to heat it, what will happen? Will the conduction become better? We'll see. Now in metals, as you can see, we have metal, positive charge and electrons. That's what the electron C model is like, okay? Now, these positive charges, which are called kernels, as I already said, they start vibrating at a much higher speed when you apply higher temperature, okay? Because of which the movement of electron is restricted, and that is why in case of metals, if you increase the temperature, okay, if temperature is increased, the conduction is decreased in case of metals. That is what happened in case of metals, okay? In semiconductors, on the other hand, if you increase temperature, of course, the conduction is going to increase because the electrons are getting energy to go to the conduction band. So this is very important to know the difference of temperature in case of metals and semiconductors. Okay. So metals, temperature increases, conductivity decreases. To sum it up, what happens in case of semiconductors is this, okay? So this is, as you can see, the energy gap is really quite less. And as and when the energy is supplied from the surroundings, which means in form of heat, the electrons from the valence band can go to the conduction band quite easily and hence become conductors or hence conduct electricity, right? They'll not become conductors as in because they'll not be very good conductors, but they will become soft conductors, okay? So now, which basically means that this is a crystal of silicon. Silicon is a semiconductor. It belongs to group 14 of periodic table. And now, as you can see, all the electrons are in the bonded situation, right? Each single bond constitutes of 2 electrons. We all know that, right? Each covalent bond constitutes of 2 electrons. And of course, every system has electrons. We know that, right? Because electrons must always be there, right? But only when these electrons are available, okay, they are mobile, they are free, which I already said, only then conduction can happen, which of course is the case with metals and not with semiconductors, right? So when we apply heat energy, which is here, the electron is going to, become free of its bond, which means the bond is going to break, and now this electron is available for conduction, and that is how we are making semiconductors conducting by applying heat, okay? This is called as intrinsic semiconductors, which are belonging to group 14 of periodic table, okay, which is silicon and germanium, okay. They're called intrinsic because they're internally semiconductors. We just have to supply some amount of energy, or we just have to increase the temperature, okay. This is what is written here. Now, what if we do not want to depend upon temperature, okay? Because even if we do that, the conduction that we get is not quite practical. It's not that much, and we cannot even use it for any purpose that we have to, right? So now we do not want to depend upon heating. And if we don't do that, that kind of semiconductors which will allow us to move ahead of heating and a better conduction are called extrinsic semiconductors. We will see how. So what do we do is we purposely add some impurity, okay? We add some impurity purposely on purpose, and this process is called doping, okay? Now, the impurity which we are going to add is not going to be actually dust particle, okay? So the impurity which we are going to add is going to be a metal only or an element only, okay? Not a metal, it's going to be an element. It can be electron rich or it can be electron deficient, okay? And depending upon whether it's electron rich or electron deficient, we will get the N-type and P-type semiconductors. Alright, so to understand the N-type and P-type semiconductors, we have a beautiful image of a periodic table right in front of us. So we don't have to remember it, okay, the entire series, we don't have to. We just have to know what is present in group 13, group 14 and group 15, okay. So these are the 3 groups which we mainly want to consider. So let's just jump on right here, okay. So we have group 13, 14 and 15, and we already know that group 14, which is this one, is having silicon and germanium, which are our intrinsic semiconductors, okay. And they have the valency of 4, which means they have 4 electrons in their outermost shell, okay. Group 15 on the other hand is having the valency of 5, which means it has 5 electrons in its outermost shell, and group 13 is having the valency of 3, which means it has 3 electrons in its outermost shell, right. Now, this is what a silicon crystal looks like, where we have different silicon atoms having 4 bonds each, 1, 2, 3, 4, okay, and the other ones are in the shared state, and all the bonds all the electrons which you see on your screen are all in the bonded situation, okay, they are not free to move, and because they are not free to move, they cannot conduct, right, okay. But what if I try to replace one of the silicon atom with phosphorus, okay, so I'm replacing one silicon with one phosphorus, that's what I'm doing here, and the phosphorus is having a valency of 5, which means it is having 5 electrons. So 1, 2, 3 and 4 electrons are used up in forming the bonds as silicon atom would do. But the 5th one is actually free, in the free state, and it can actually be used to conduct electricity, right? In this type of semiconductors, we are doping an impurity of group 15, okay? And as a result of which we have extra electrons available or negative charges available for conduction, we call it as N-type semiconductor, because conduction is because of the presence of negative charges here, okay? Alright. Now, if the same thing we do with the group 13 element, okay? So in case of group 13 element, we know the valency is 4, which means they are forming 3 bonds, okay? Because, the valency is 3 because they form 3 bonds, okay? Now, if I replace one silicon atom with a boron, right? So it only has 3 electrons. 1, 2, 3. These 3 are used up in formation of bonds, whereas one place is left And this one place which is left is called a hole, which is positive. Why is it positive? It's not actually having a positive charge because it is a deficiency of electron, it is called a positive hole, right? So when the conduction happens because of positive holes, we'll discuss how that happens. That is called a P-type semiconductor. Now let's see how these holes are able to conduct. Well, the holes, when they conduct electricity, it's mainly because of electrons only, because these holes are just vacant spaces where electron wants to jump, okay? And because electron jumps to, from one hole to another, that actually causes the movement of electrons, and that's why holes are also able to conduct electricity, right? So that's what your holes are, and that's what the conduction is like in the P-type semiconductors. So we have completed what are the conductors, what are insulators, what is the valence band theory, the N-type and P-type semiconductors. Coming to the applications of it, we have a variety of different applications of semiconductors, resistors, capacitors, diodes, transistors. Well, a number of applications I can list, which on the screen you have even less. Okay, so it's quite an evolving field still. So you can do the research if you want to later in life. Whenever I go on a vacation, okay, and I pack my things, it looks something like this, and I think this is the case with everybody. But when I'm coming back from that vacation and I have to pack the same things in the same bag, okay, it looks something like this. And please don't tell me I'm the only one in this. Please don't tell me, because I know it's not the case. So has the space altered? No, the space is the same. The amount of clothes is the same. Okay, the amount available in my suitcase is the same. So what is the difference? The difference is in the packing, and that is what we are going to study today, the packing efficiency. So of course it's quite clear that the first one is a more efficient packing, okay, and efficient packing basically means a better packing because we are able to pack more amount of things in the same space, is basically what is the efficient packing, okay? So now we'll just extrapolate this concept to our solid state and the unit cells which we have studied priorly. And if you have not done that, you should definitely do that, because for this video, what we should definitely know is what is the unit cell, how many types of unit cell exist, and what is the number of atom in each unit cell, okay? So coming to the type of unit cells, we have three different types of unit cells, which is simple cubic, face-centered cubic, and body-centered cubic unit cell. All these three are cubic, which means the basic structure is of a cube, okay? In simple cubic, we have the lattice points or lattice sites only at the corners of the unit cell, okay? Which means a cube has 8 corners, so we have 8 different unit cells, 8 different atoms in this unit cell, but each unit cell is also being shared by 8 different atoms around, so the total number of atoms here in the unit cell of simple cubic is 1, okay? So which means one unit cell is having a total of only 1 atom, right? In case of face-centered, we have, in addition to the ones present at the corners, just like in simple cubic, okay, we have atoms present at each face of your cube. And of course, you know that a cube has 6 faces, which means it should have 6 extra atoms there, but each face is also shared between 2 other cubes. So we have a total of 3 plus 1, which means 4 atoms in this unit cell, okay? In body centered, we have, in addition to the ones present at the corners, we have 1 extra which is present inside your unit cell, okay? And this is not shared with any other unit cell. So this is just belonging to the unit cell it is present in. So it is 1 plus 1, which means it is 2, okay? So number of atoms per unit cell is 2 in case of body centered, 4 in case of face centered, and 1 in case of simple cubic unit cell. And now we can talk about the packing, okay? So packing efficiency, what is packing efficiency? As I already told you about my example of packing our bags at the vacation, which is, I think, a never-ending problem, right? So packing efficiency is nothing but the percentage of total space occupied by the particles in a unit cell, okay? So if I'm occupying all the space available, my packing efficiency is going to be 100%. But we know that 100% never exists. No matter how much we try to do, some space is always going to be left, okay? So packing efficiency can never be 100, understand that. But what is the packing efficiency for all these 3 different unit cells? We'll see that in a while. Okay, so what is packing efficiency? Packing efficiency in mathematical terms is the volume occupied, okay, by the atoms of the unit cell. And these atoms can be 1, 2 or 4 depending upon whatever type of unit cells it is, okay, divided by the total volume available. So total volume available is of a cube, because all these 3 are basically cubes, right? Simple cubic, face-centered cubic, body-centered cubic. So total volume of the cube. multiplied by a factor of 100, because why 100? Because of course packing efficiency is a percentage, so we have to multiply by 100, and whatever answer we get is going to be in percentage, right? So now we'll start with the first one, which is the simple cubic unit cell. Alright, so let's try to see what happens in a simple cubic cell and find out the packing efficiency of it. As we already know that lattice sites are only at the corners, okay? And if I just write the formula, we have packing efficiency as the volume of one atom, because in this case we only have one atom, right? Divided by the volume of cube, okay, into 100. Now, if this is the cube, we can consider the side length or edge length of this cube to be equal to A, because we don't exactly know the value of it. So we'll just assume it that it is A, which is a variable, okay? So what is the volume of a cube? Volume of any cube is always side cube, okay? So it's A into A, which is A cube. This is the volume of the cube, right? So we have the denominator with us. Now we have to work on finding the numerator. Now what is the numerator? Numerator is volume of one atom, okay? So atom is considered to be a sphere, although atom is not exactly a hard sphere, but because for the easiness of our calculation, we'll consider the atom to be spherical, okay? And what is the volume of sphere? It is 4/3 pi r cube. So we have the numerator with us, we have the denominator with us, we will just multiply by 100 and we should be getting the value, but there is one issue. What is the issue? The issue is that we have two variables here. We have r as a variable, we have a as a variable, and we cannot solve any further unless we establish a relation between a and r. So let's do that, okay? So if I look very carefully in the structure of your simple cubic cell, I can very clearly notice that this is my radius, okay, of one atom, which is r. Okay, and this is my one radius, this is my two radius, this is one again my radius, and this is again my radius, okay? So total 4 radius, if I just combine, it is one edge length, which is a, okay? So which means 4 times radius of the atom is equal to a, that is the edge length. Eureka! We have a relation between the two variables which we had, which is r and a, and we can substitute that in our equation and we can find out the value, okay? So if I just try to solve it further, we have 4/3 pi r cube divided by a cube, and instead of writing a cube, I can just write 4r cube, alright, into 100. And if I solve this, I will be getting the value 52.4%, and this is my packing efficiency in case of simple cubic unit cell. So only 52.4% is filled, rest all the space is empty. So for a simple cubic unit cell, packing efficiency not so high. Okay, so now let's see what happens in case of your face-centered cubic cell. Let's begin. Well, the same thing is there. We have the formula of packing efficiency as nothing but volume of atoms, okay, which are present in the unit cell divided by the volume of total volume available, which is volume of the cube, okay, multiplied by 100, and it's quite easy. Again, we'll do the same thing. We'll just assume that the edge length is equal to a. So the denominator is a cube, which is sorted. Now we'll only talk about the numerator, which is the volume of the atoms. Well, we have again not here, in this case, we have not one, but we have actually 4 atoms in the unit cell. So whatever is the volume of one atom, we'll just multiply that by 4 and we'll have the numerator, right? So now again the same thing, we have to establish a relationship between a and r so that we can find out the answer to what our packing efficiency is. So now if I look at this, these 3 different atoms which are connected, okay, the atoms which are on the face, okay. Now if I just connect these 3, I can see that they are made up of 4 times my radius, because the first one is the entire atom, so it is 2 times radius. Second one is 1 radius, and third one is also 1 radius. So we have r plus r plus r plus r. We have 4r. Okay, so this is the if we just cut a diagonal from the side of the sphere. So now we discuss about what happens in the face-centered cubic cell. The exact same thing happens. The packing efficiency is nothing but volume of atoms, okay, which are present in the unit cell divided by total volume which is available, which is the volume of the cube, multiplied by 100, and that's that. Now in the numerator, now we have not 1, not 2, but actually 4 atoms, okay, because in face centered we have 4 atoms per unit cell. So whatever is the volume of one atom, we'll just multiply that by 4 and we will have our numerator. The denominator is simply, we'll just again assume that our edge length is A, and we have A cube as the denominator, which is the volume of the cube which is present. Okay, now if I talk about the numerator, which is volume of the atoms, again we have to do the same thing, which is we have to find a relationship between R and A so that we can solve our two variables and we can get the answer. So let's try and do that. Now if we look at these three spheres, sphere 1, sphere 2 and sphere 3, these are directly connected. Okay, they are connected and they are not having any space in between. So if I just look very carefully, this is my radius R. Okay, again this is R, and again this is R because diameter is 2 times radius, and again this is R. Okay, so this entire length, okay, is nothing but 4 times R, or 4 times the radius. And we already know that edge length, this edge length is A, and this edge length is also equal to A. If I look very closely, you can see a triangle which is formed, and what happens when we have a triangle, we apply something called the Pythagoras theorem. Okay, now what does Pythagoras theorem says? This says that whenever we have a right angle triangle, okay, then the hypotenuse square, hypotenuse is the longest side, okay, the hypotenuse square is equal to the addition of the two different sides, the squares of the two different sides. So we have a square plus a square is equal to hypotenuse square, right? So we'll just put it here. We have a square plus a square is equal to the hypotenuse square, which we know is 4r, okay, which you already have discovered. So it's 2a square is equal to the hypotenuse square. We'll just do the root on both sides. We get under root 2a is equal to the hypotenuse, which is equal to the 4r, which we already know. Now this under root 2a is equal to 4r is the relationship which we were actually looking for, and now we have the relationship between r and a, and we can apply this into a formula. And when we do that, okay, which is the formula is 4 by 3 pi r cube into 4 divided into 4 because we have 4 atoms per unit cell, divided by the edge length a cube. Now a can be written as 4r by under root 2, okay, cube into 100. And when we solve this, we get the answer as 74%, which is very high. So if we compare the packing efficiency of face-centered cubic to a simple cubic unit cell, we already know that face-centered is having a very high value. Okay, it's 74. The other one was 52%, if you remember, right? So now we'll talk about the last one, which is the body-centered. So now let's finally talk about what is the body-centered cubic cell and the packing efficiency of that, and we'll be good to go. Now we know what we have to do. We just know that this numerator, which we have total volume occupied by the atoms, which in this case is 2 because we have 2 atoms per unit cell in case of body-centered lattice, okay, and denominator we have the total volume of the cube, which is a cube, which we already know, and multiplied by 100 we'll get the answer. So let's just cut to the chase. We have to find a relationship between a and r, and that's what we have to do. Now if we find out the relation between a and r, in this case we have to find the spheres which touch each other so that we can establish a 4r relation, okay. So the 4r relation which we used in our simple cubic is this, okay. This side we established as 4r because the spheres were touching each other, which is not the case here, okay. In your face centered we established a relationship here because these 3 spheres were touching each other, which is again not the case here because the orange one is in between the unit cell. Now in the body centered, the 3 spheres which actually touch each other are these 3. The one at the lattice side, this one in between, and the one again at this lattice side, okay. I'll just draw it again. So these 3 spheres are the ones which are actually touching each other. This one, okay, the middle one and the corner one, okay. So even though in the picture it seems it's not touching, but they're actually touching each other. So this is the 4r which should be there, right? So again we'll be using the Pythagoras theorem which we used before, but now we have 2 different sides which we have to take into account. If we look at these 3 sides, let's see, okay, this is our body diagonal, okay, this is our A, and this is the another side. So you see the difference in triangle. The triangle which we took in face centered and triangle which we're taking here are 2 different triangles, right? So this is 4r. This we already know is A, okay, which is the edge length. What is this? This side is nothing but the hypotenuse of this and this side, right? So we know this is nothing but a square plus a square, right? This is 2a square. Clear? So if we just put the Pythagoras theorem, we can very clearly see that a square plus 2a square is equal to our hypotenuse square, which in this case is 4r. So we have 3a square, okay, is equal to the hypotenuse square. So if you just do the root on both sides, we have root 3a is equal to 4r, and eureka, we have a relation now. And as and when we put this into our formula, we have 4 by 3 pi r cube into, in this case 2, because we have 2 atoms per unit cell, divided by a cube, and instead of a we'll be writing 4r by under root 3 whole cube multiplied by 100, and if we solve it, we get the answer as 68%. Okay, I'll just write it here. We get the answer as 68%, and 68% is the total packing efficiency of a body-centered cubic cell. And if we just compare all these three, okay, so in simple cubic we have 52.4%. Okay, in body-centered cubic we have 68%, and in face-centered we have 74%, which means face-centered is the best packing, is the most efficient packing, and that is what was the point of this video, to understand the packing efficiency of all these three, to establish a relationship between A and R, which will be of course used for the formulas later on. So what we know as of now is that in case of crystalline solids, everything should be very perfect. The arrangement of constituent particles, which can be atoms, molecules, and ions, they should be perfect, right? Something like this is what we imagine, right? But in reality, it's not like that, okay? Perfection is okay. I mean, solids should be perfectly arranged, ordered structure, long range order should be there. But this does not happen unless and until it is 0 Kelvin. Only at 0 Kelvin will you observe that, okay, fine, the particles are at whatever space they should definitely be at, right? But in the real case scenario, in the scenario which we see around all of us, we have something called defects. Okay, what is a defect? Defect is something which is just a deviation from the ordered arrangement. That's called a defect, okay? And these defects or these imperfections are going to actually give new properties to a solid. We'll see all that how, but you just need to know that, right? Okay, so these defects are of three types if we just classify them. Stoichiometric defects, impurity defects, and non-stoichiometric defects, okay? And it's important to know that all of them are included into the point defects category. So what is a point defect? Whenever in a crystalline lattice there is a defect at points, okay, which is at lattice points, that defects are called as point defects. Whereas when we have defects in the entire line of, you know, atoms or molecules or ions, that is called a line defect, which is not going to be part of this video today, which means we are going to be only discussing the point defects here. Okay, so if we talk about the stoichiometric defects, okay, well, these will not destroy the stoichiometry of the solid. Now, what is stoichiometry? So if we just, if I just write over here, NaCl, okay, which is salt. So if I write NaCl, which means for every one sodium ion, there should be one chloride ion. This is the stoichiometry of this NaCl solid, okay? And but if there's any less sodium ions present or any higher amount of sodium ions present for one chloride ion, that is going to be a wrong stoichiometry, okay? So these defects will not play with the stoichiometry, and they are also called thermodynamic defects or intrinsic defects. All right. Now, these are of two types, that is vacancy defects and interstitial defects. Well, I think it's very clear with the name that vacancy defect is something which is going to be like maybe at some point, at some place in a solid, in a lattice point, there should be some atom, molecule, or ion, and it is not there. It is a vacant place, and that is what a vacancy defect should be. And interstitial means that instead of being at a lattice point or lattice site, it is there somewhere in between. So we'll discuss all that in detail. I'm just saying all this, in a flow, but we'll discuss all this in detail, okay? All right. But electroneutrality should always be maintained. So no matter what defect we're talking about, stoichiometry, impurity, or non-stoichiometry, we do not get an electric shock when we touch salt. Do we? I don't think so, okay? So which means because of course if salt is electrically neutral, it is not having any excess charges, means it is electrically neutral and it is not going to give us a shock if we touch it, right? So which means everything which we see around us is electrically neutral, we just don't get a shock touching anything, right? So which means every defect is going to be will be accepting the fact that electroneutrality should be maintained, and no defect is going to contradict that. Alright, so let's discuss what are these Frenkel defects, okay? This is what a perfect crystal looks like. Perfect or close to perfect, because we know how perfection is something which is not achievable. So this is what a close to perfect crystal looks like. Now, it's possible for these cations, the orange ones. So I'm calling these orange ones as cations because they're smaller in size, and the bigger ones as anions because, well, they're bigger in size. And you should know why, okay? If you do not know it, then you can comment that down below. I'll try to answer that, but that's the case now. Now, it's possible for these positive charges to move or to dislocate from the point that they are present in to a new point in the crystal or the interstices of the crystal, something like this. Okay, so this place where the cation was initially present, it has moved from this place to a new place here, and now from the point it has moved this place, okay, there's a vacancy that is created. So here we have a vacancy defect, okay, and to the place which it has now moved, okay, now we have an excess cation there, okay, so that is an interstitial defect. So what we have already discussed, we have two types of defects, vacancy and interstitial defects. Frenkel defects is actually a combination of both. We have vacancy at the point where it should have been present, and interstitial defect at the point where it is now present, right? Okay, so in case of Frenkel defects, it is also called dislocation defect, because very clearly it's just nothing but a dislocation of the cation from one point to another, right? Second thing is, it does not change the density. Why will it change the density, right? Because density depends upon mass and volume, and because there is no change in mass, because whatever the mass was initially there, it's still that mass only, because it's just a dislocation, okay, not a complete vacancy. It's a dislocation from one point to another, so mass is exactly the same. So density, of course, is not going to be affected, okay. And then it can only exist when there's a large difference between the cation and anion. Of course, okay, if the cation is really small, only then it can, be moving from one place to another. If it's big enough, how will it move, right? So if it's big enough, just like an anion, then it is not going to be free to move, and the Frenkel defects would not take place. But since it is small, only then it is able to move. So it is only possible, Frenkel defects are only possible when there is a large difference in the size of cations and anions. Now we have examples like ZNS, AgCl, AgBr, AgI. Okay, so you'll notice that I have highlighted AgBr in a while. You'll know why. Okay, so all these different solids have a higher difference in the sizes of cations and anions. That's why we have Frenkel defects there. Now let's understand what is Schottky defects. Before that, we should know that electron neutrality is always maintained, because whatever it's just shifting, it's just dislocation. There's no alteration in the charge. Okay. Now we have Schottky defects. What is the Schottky defects? This is a perfect crystal. Again, in case of Schottky defects, we have a close to perfect crystal. Okay. Now, what if there is a vacancy of a cation? Okay, and vacancy is complete vacancy. The cation is actually out of the crystal now. It's not even there somewhere in the interstitial area. It's completely out. Okay. If that happens, then the solid will have an excess negative charge, because if one cation is gone, there will be one extra negative charge, and as and when we touch the solid, we'll be getting electric shock. But that does not happen, right? So that is why whenever there is going to be a cation less, the same number of anions have to move out of the crystal so as to maintain electrical neutrality, right? Which is a rule which we have to always follow. So what will happen is, whenever a perfect crystal is there and there is one anion which decides to, or cation which decides to move out, there will be the same number of anions which will definitely have to move out, and that is what a Schottky crystal looks like. Okay. Okay. This is nothing but just a vacancy defect in ionic solids. It's complete vacancy. There's no interstitial defect here. It's only vacancy defect here, unlike in case of Frenkel defects. It decreases the density, of course, because now we have a decrease in the mass, because we have one cation, one anion less. In this case, we have only one less, but in actual case scenarios, we have like a number of cations and ions which are completely gone out, right? So now it exists in examples like NaCl, KCl, CaCl, and again AgBr. So now AgBr is one example, which is an example of both Schottky as well as Frenkel. This is something which can be asked in competitive exams. That's why it is highlighted. Thank you so much. All right. Again, electron neutrality is always maintained, and because of that, we have, how one cation is gone and one anion, of course, has to go. So that's what is also accepted here. All right. Next, we have impurity defects. The second type of defects is called the impurity defects. Now, this is what an NaCl crystal looks like. Okay, so we have Na and Cl. The stoichiometry is something like this: NaCl. Na is having +1 charge and Cl is having -1 charge. Okay. Now, Strontium is another element which is having a charge of +2. If I decide to replace some sodium positive ions with strontium ions, okay, since strontium is having a charge of +2, unlike your sodium which is having a charge of +1, if it is trying to replace sodium positive, then of course 2 sodium will have to go out, okay, so as for 1 strontium to come in. Is that clear? Because of course electrical neutrality, our rule has to be maintained, okay. So because here 2 will have a charge of +2, only 1 has a charge of +2, so to electrical neutrality, to maintain that, we need to have that 2 sodium have to go out in place of 1 strontium which is going to come in, okay. So if I replace 1 sodium with strontium, 1 extra sodium has to go out, and that place is going to be vacant, right? This is vacancy which is created because so as to maintain electrical neutrality. So this is called impurity defect, in which we are adding another element as an impurity into our existing solid, and it is a vacancy defect at the cationic sites. Each strontium plus is replaced by 2 sodium +1, because of course to maintain electrical neutrality, and examples are CdCl2 and AgCl. The same thing is going to happen if you just add AgCl crystals into CdCl2 crystals, right? Okay, now we have non-stoichiometric defects. Again, non-stoichiometric defects are going to play with the stoichiometry. They are not going to be in accordance with stoichiometry. They will definitely be changing the stoichiometry of the crystal. Let's see how. So this is NaCl, okay. NaCl, as I already discussed, Na is 1 and Cl is also 1. So for every 1 Na, there should be 1 Cl, and if it's any less or any higher than that, of course the stoichiometry is not right, okay. Na here is the metal and Cl, chloride, here is the non-metal, okay. Now, these defects can be of 2 types. Metal excess, either the metal can be excess, okay, in this case it is 1:1, but maybe it is higher than 1, so it is going to be metal excess, or it is metal deficient. In this case, maybe it is going to be less than 1 and Cl is going to be 1, so that's metal deficient defect. Okay, let's talk about the metal excess defects. In metal excess defects, also it can be of 2 types. It is anionic vacancies. If there's anions are going to be less, of course metal is going to be high, right? So that is going to be one case. And second is extra cations. Of course, if cations is going to be high, it means metal is high. Okay, so again the main rule is followed. Electroneutrality always has to be maintained no matter what. Now this is what a sodium chloride crystal looks like, okay. Now if we are going to heat it in presence of sodium vapor, what happens is, so this is sodium vapor, right? Now sodium vapor is having sodium atoms. Now sodium atom is never stable. It is always going to convert into sodium plus and 1 electron, because it has to do that. It is something which is tendency, okay. Now what happens is, when sodium is present, it is going to convert into sodium plus ion, and 1 Cl chloride, okay, from the lattice is going to move from here to this sodium so as to form sodium chloride there, okay. Now this sodium, to form sodium chloride, this is already Cl minus, okay. To form sodium chloride, this sodium has to become Na plus, okay. So it is going to give out 1 electron, and that 1 electron is going to go and sit there at the site of vacancy of the chloride, okay. And this site is called as F center or Farbenzenter center. This is something which is asked mostly in the competitive exam, so you can highlight that. And because of this F centers, it imparts some color to the sodium chloride when it is heated. It becomes yellow in color, okay. So the reason of the yellow color is because of the F center, and when we heat it, what happens is these electrons are excited, and when they come back to original state, they give out some light, and that is what you see as the yellow color, okay. The same thing happens when lithium chloride is heated, okay, pink color you can see, and when KCl is heated, you see violet color. That's why you see a beautiful image on the first slide of this video. Actually it's a GIF where you see different solids being heated, right? Okay, again these are anionic vacancies, okay. Okay, so now let's have a look at what happens when there are extra cations. So we have done when there is less number of anions, okay, as an example of NaCl and F centers, we have done that. Now let's see what happens when there are extra cations, okay. So the most important example is zinc oxide heating. So when zinc oxide, which is white in color, okay, when it is heated, it becomes yellow, okay. The reason for it becoming yellow is this, that when it is heated, it loses oxygen. So this oxygen is lost and it is gone in air, and what we have is, we have extra amount of zinc 2+ cations and the electrons, and both of them go into the interstitial sites, okay? And when they are heated, these electrons are excited, and when they come down to the lower energy state, they give a color, okay? So I don't think it's a rocket science here. The most important example here is zinc oxide and its heating, and that is an example of extracations defect. Now we have the last one, which is metal deficiency effect. So we have done what is metal excess defect of two types, anionic deficiency and extracations. Now we have metal deficiency defect. Now, metal deficiency defect is kind of an inherent defect because it is something which is made, it is something which comes at the time of making of the crystal. So when we make ferrous oxide, FeO, okay, we know ferrous iron is present in two oxygen state, which is +2 and +3, right? So when we are trying to make ferrous oxide, which means Fe2 plus and oxygen O2 minus, okay, at that time, from the making of the crystal, it is very difficult to keep the stoichiometry 1:1. Okay, according to the formula, it should be 1:1, okay, but it is mostly not that, and mostly iron is always less. Fe2 plus is always less, okay. This is something which is inherent, okay, and this gives rise to the metal deficiency defect, okay. So this is the most important example here of FeO crystal, and this was all about impurity in stoichiometry, impurity in solids. So we all have in our lives at some point interacted with magnets and basically had our fun with magnets, right? So what is the exact definition? The exact definition of a magnet is anything that is producing a magnetic field or is attracted to a magnetic field is called a magnet, okay? Now we have a basic and a vague idea to what could or could not be a magnet. For example, we would not expect paper or wood, okay, to be attracted to a magnetic field, but we would expect, let's say, a coin of 1 rupees to be attracted, okay. So let's just extrapolate this knowledge of magnetism to the solid state chemistry. So we know how solids are made up of constituent atoms, molecules and ions, right? Now considering that this solid is made up of constituent atoms, okay, the constituent particle is an atom. Now after moving to an atom, we know how atoms also are made up of its subatomic particles, which are electrons, protons and neutrons, okay. Now this subatomic particle, which is called an electron, is the main reason why I have to make this video today. Well, electron is the reason why solids can be magnetized, and we'll see how. This electron is actually a charged species, right? So this charged species called electron, which is having a negative charge, is showing two types of motions, because of which we can call this a teeny tiny magnet, okay? What are these motions? Let's discuss. The first one is the orbital motion of electron. We know how electrons are rotating around the nucleus, right? So whenever a charged particle is moving, it creates its own electric and magnetic field, right? So because it is moving around, not moving actually, but rotating around a nucleus, it is having its own magnetic field. The second reason is the spin motion of electron. This again is another type of motion which the electron is showing, which is around its own axis, and this is also the reason why it has its own magnetic moment, okay. So the electron is having its own magnetic moment, or we can say that it behaves like a magnet, okay, because of two main things, which is the first one is orbital motion of an electron around the nucleus, and second one is the spin motion of an electron around its own axis. Now well, we need to know what is a Bohr magneton, right? So we know how every charged particle should be having its own magnetic field, okay. Now every electron in a system, because in a system we don't have 1, 2, 30 or 40, but millions and trillions of electrons, right? But every electron in a system is having some amount of magnetic moment associated with it, and that amount of magnetic moment is called the Bohr's magneton. As you can see, the value is quite less. It is 9.27 into 10 to the power minus 24, okay, ampere per meter square, which is quite less, okay, but because this is just the magnetic moment of just one electron. Moving on, the solids are actually classified on the basis of this magnetic behavior into these 5 categories. First one is diamagnetic, second one is paramagnetic, then we have ferromagnetic, anti-ferromagnetic and ferrimagnetic, okay. We'll discuss one by one what are these and how do we classify solids into these categories. Let's begin. So now, as I already said, that electrons are behaving like magnets, okay. Now these magnetic moments of electrons are just arranged randomly inside a solid, okay? And the behavior of these magnetic moments as and when a magnetic field is applied to it will tell us which category they belong to, okay? So what could happen is that if we apply the magnetic field to this randomly arranged arrangement of the magnetic moments, the first thing that would happen is that they will arrange themselves in direction of magnetic field, okay? And if these magnetic moments do that, then we say that the particle is magnetized, okay? Or it could also happen that these magnetic moments, instead of arranging them in direction of the external magnetic field, they will arrange them opposite to the direction of magnetic field, okay? And in this case, we can say that they are repelled by the magnet, or they are opposite to what we call being magnetized, okay? So having all the basic idea, we'll start with what are these different definitions, and we'll start with the first one, which is called diamagnetic, okay? So in a diamagnetic, the first, I would say the first criteria of being magnetized is having an electron, okay? Now every system is having an electron, that is for sure, okay? Because if there's no electron, of course there should be no atom, but that's not the case anywhere. Now in any system, if we talk about, okay, we know how in an orbital electrons are present like this, which means one is having an upper spin and the second one is having a lower spin, which is minus half, okay? Now these two, when they are present together, they cancel each other out because they are having opposite magnetic moments. That's complete, that's very obvious, right? And the net magnetic moment is going to be 0, right? So in any system, if we are having only paired electrons, okay, every electron is present in its pair, okay? Let's say we have plenty of electrons, but all of them are present in pairs. Then all of them will be cancelling out on the magnetic moments, and the net magnetic moment is going to be 0. And that is the case with diamagnetic materials, okay? They're having 0 magnetic moments because all the electrons are paired and there is no unpaired electron present, okay? So the main examples which you guys have to remember, which is something which can be asked in exams, are salt and water, okay? And also some other examples which you see around yourself, which of course wood, okay? All these are diamagnetic substances. They can never be magnetized. Moving on to what is paramagnetic. Now what is paramagnetic materials? Now these materials do have electrons, okay? They have unpaired electrons present, which can be 1 or more than 1. Now these substances are weakly attracted by magnetic fields. Why? Because of course the randomly arranged magnetic moments are maybe arranged in direction of magnetic field as and when the magnetic field is applied, but also the main thing is that they will lose their magnetism as soon as the external magnetic field is removed, okay, which is not the case with something which we will see further. The paramagnetic substances will become magnetic as and when we apply an external magnetic field, but will lose the magnetism as and when we remove an external magnetic field, okay? So the most important example here is oxygen, and this is something we should know, okay? So we have this topic of valence bond theory, which we do in class 11th, I guess, and there we study how the electrons are filled inside inside the orbitals or inside the molecular orbitals of oxygen gas, okay? And that is where we realize that oxygen actually is paramagnetic, and now we know the reason why it is paramagnetic, okay? Because it is having one unpaired electron in case of if we talk about only oxygen. Now we have ferromagnetic substances. Now what is the case of ferromagnetic substances? These substances are attracted very strongly by magnetic fields, okay, and they are permanently magnetized. So unlike what happened in case of paramagnetic, okay, they are permanently magnetized, and the magnetic moments are arranged completely in direction of the magnetic field which is applied, okay? So it may be possible, it may be a possibility that the magnetic moments are arranged just like this, okay? So they are arranged almost, maybe in direction. Something is like this, something is like here, something again in direction, then something is here and there, and this something again in direction. So this will create a net magnetic moment, okay, which is not going to be very high, but still going to be there. So that's why it is written weakly attracted, right? But in case of ferromagnetic, as you can see, all the magnetic moments are arranged directly in the direction of the external magnetic field, and that is why they are very, very strong magnets, and they are permanently magnetized, okay? They will remain magnets even after the external magnetic field is removed. That's what ferromagnetic are, okay? And the main examples are metals, strong metals like iron, cobalt, nickel, gadolinium, and this is a very important example of chromium dioxide, which you guys have to remember, okay? There's no doubts about that. Now we have anti-ferromagnetism. What is the anti-ferromagnetism? So as the name suggests, okay, there's something anti going to be about these ferromagnetic substances. Now here the magnetic moments are arranged in anti-parallel direction, which results in zero net magnetic moment. So as you can see, they are arranged. They should have been arranged directly in direction of the external magnetic field, but okay, there's one, as you can see, there's one above, there's one below, so they are cancelling out, then they are cancelling out, then they are cancelling out. Just like that, all of them will cancel out each other, and we will have a net zero magnetic moment, and that's why they are not attracted. Okay, so they should be having ferromagnetic characteristics, but because of the anti-parallel arrangement of magnetic moments, the net magnetic moment that we get is zero. So that's the case here. And the most important example is this, which you definitely have to remember, manganese dioxide, a very important example which is definitely, asked in exams. So do remember this, okay? And the last one which we have is ferrimagnetic materials. Now what is ferrimagnetic materials? Okay, in case of ferromagnetic and anti-ferromagnetic, we have two extremes, okay? In case of ferro, we have all of them directed in direction of magnetic field, and in case of anti-ferro, we have one is above, one is below, and net we have zero. Okay, in case of ferrimagnetic materials, okay, what happens here is that they are arranged into parallel and anti-parallel direction, but in an unequal way. Okay, and because of that, we will have a net magnetic moment. In case of anti-ferro, we have arranged in parallel and anti-parallel in equal manner. Okay, that's why we do not have any net magnetic moment, but in this case they are arranged in unequal ways, and that's why we will definitely have a net magnetic moment. As you can see here, we have two in the upward direction, one in the lower direction, then again two in the upward direction, then one again in the lower direction, and then we have finally a magnetic field into the above direction, right? So these are the examples of ferrimagnetic substances which you need to know of. Okay, and this we have a small summary as to what is paramagnetic, anti-ferromagnetic, ferrimagnetic and ferromagnetic substances, and this is something which is important and we can remember by. So you can just screenshot this slide and keep it with yourself for maybe revision purpose. And thank you so much for watching. If you have any doubts in this video, you can comment that down below. For more videos like this, follow this page and stay tuned for more.